Atoms and Molecules, Grade 9 Science, Chapter 3. Hello to all the amazing viewers out there. May God bless you. Before we move ahead, don't forget to subscribe to the channel. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India, around 500 BC. An Indian philosopher, Maharishi Kanat, postulated that if we go on dividing matter, which he called Padarth, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pakudu Katyayam, elaborated this doctrine and said that these particles normally exist in a combined form which gives us various forms of matter. Around the same era, ancient Greek philosophers Democritus and Lysippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided any further. Democritus called these indivisible particles atoms, meaning indivisible. All this was based on philosophical considerations and not much experimental work to validate these ideas could be done till the 18th century. By the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Antoine L. Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combination. Let's see the laws of chemical combination, which were established after much experimentations by Lavoisier and Joseph L. Proust. Law of conservation of mass. Tell me one thing. Do you think there is a change in mass when a chemical change takes place? Let's perform an activity. X and Y are two sets of chemicals. Set X contains copper sulfate 1.25 grams, barium chloride 1.22 grams, and lead nitrate 2.07 grams. Set Y contains sodium carbonate 1.43 grams, sodium sulfate 1.53 grams, and sodium chloride 1.17 grams. Now prepare separately a 5% solution of any one pair of substances listed under X and Y, each in 10 ml of water. Take a little amount of solution of Y in a conical flask and some solution of X in an ignition tube. Hang the ignition tube in the flask carefully. See that the solutions do not get mixed. Now put a cork on the flask. Now weigh the flask with its contents carefully. Now tilt and swirl the flask so that the solutions X and Y get mixed. Weigh them again. Now we need to consider these questions. What happens in the reaction flask? Well, a chemical reaction takes place in the reaction flask. Now, how can we confirm that a chemical reaction has happened? Well, there are 4 signs that a chemical reaction has occurred. There is a change in color. There is a change in temperature. There is a formation of a gas. And there is formation of a precipitate. A precipitate is a solid that forms when two liquid solutions are mixed. Now, why did we put a cork on the mouth of the flask? Well, we must put a cork because if in the given chemical reaction gas is produced, the gas should not escape the flask. Gas has some mass which we would want to take into account while calculating the total mass after the chemical reaction. Does the mass of the flask and its contents change? Well, we would note that the weights of the flask and its contents do not change before and after the reaction. Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. Next is the law of constant proportions. Lavoisier, along with other scientists, noted that many compounds were composed of two or more elements, and each such compound had the same elements in the same proportions, irrespective of where the compound came from or who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1 is to 8, whatever the source of water. Thus, if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio 14 is to 3 by mass, whatever the method or the source from which it is obtained. This led to the law of constant proportions, which is also known as the law of definite proportions. This law was stated by Proust as in a chemical substance, the elements are always present in definite proportions by mass. The next problem faced by scientists was to give appropriate explanations of these laws. British chemist John Dalton provided the basic theory about the nature of matter. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later, he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics, and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportions. According to Dalton's atomic theory, all matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. The postulates of this theory may be stated as follows. All matter is made up of very tiny particles called atoms, which participate in chemical reactions. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Atoms of a given element are identical in mass and chemical properties. Atoms of different elements have different masses and chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. The relative number and kinds of atoms are constant in a given compound. You will study in the next chapter that all atoms are made up of still smaller particles. For example, in a reaction, 5.3 gram of sodium carbonate reacted with 6 gram of acetic acid. The products were 2.2 gram of carbon dioxide, 0.9 gram water, and 8.2 gram of sodium acetate. Now we need to show that these observations are in agreement with the law of conservation of mass. In the given reaction, sodium carbonate reacts with acetic acid to produce sodium acetate and carbon dioxide and water. Now, total mass on the left hand side is 11.3 grams, and so is the total mass on the right hand side. Thus, it is in agreement with the law of conservation of mass. Hydrogen and oxygen combine in the ratio of 1 is to 8 by mass to form water. So, what mass of oxygen gas would be required to react completely with 3 gram of hydrogen gas? We know that for every 1 gram of hydrogen, 8 gram of oxygen is required. Therefore, for 3 gram of hydrogen, the quantity of oxygen required would be 3 times 8, which is 24 grams. Before moving ahead, let's discuss a couple of questions based on Dalton's atomic theory. Can you recall and tell which postulate of Dalton's atomic theory is the result of the law of conservation of mass? If yes, let us know in the comment section below. If not, don't fret. Let's cover it again. The postulate of Dalton's atomic theory resulting from the law of conservation of mass is the relative number and kinds of atoms are constant in a given compound. Atoms cannot be created nor be destroyed in a chemical reaction. Okay, now try to answer this. Which postulate of Dalton's atomic theory can explain the law of definite proportions? The relative number and kinds of atoms are equal in given compounds. If you're liking the video, don't forget to hit the like, share, and subscribe button.
Moving on to the next topic, let's discuss what is an atom. Have you ever observed a mason building walls? From these walls, a room and then a collection of rooms to form a building? What is the building block of the huge building? What about the building block of an anthill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. Have you ever wondered how big are atoms? Atoms are very small. They are smaller than anything that we can probably imagine or compare with. More than millions of atoms, when stacked, would make a layer barely as thick as a sheet of paper. Atomic radius is measured in nanometers. 1 by 10 raised to the power 9 meters is 1 nanometer. We might think that if atoms are so insignificant in size, why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surfaces of elements showing atoms. This is an image of bulk silicon surface. Let's see what are the modern day symbols of atoms of different elements. Dalton was the first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element. That is, one atom of that element. Berzelius suggested that the symbols of elements be made from 1 or 2 letters of the name of the element. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from English word meaning yellow. Nowadays, IUPAC, which is International Union of Pure and Applied Chemistry, is an international scientific organization which approves names of elements, symbols, and units. Many of the symbols are the first 1 or 2 letters of the element's name in English. The first letter of a symbol is always written as a capital letter and the second letter as a small letter. For example, hydrogen is H, aluminium Al, and not capital A and capital L. Cobalt is capital C and small o. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Examples are chlorine is capital C followed by small l. Zinc is Zn. Other symbols have been taken from the names of elements in Latin, German, or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from natrium. Potassium is K from kalium. Therefore, each element has a name and a unique chemical symbol. Here are the names of some elements with their symbols. Atomic mass. The most remarkable concept that Dalton's atomic theory proposed was that of atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportion so well that scientists were prompted to measure the atomic mass of an atom. Since determining the mass of an individual atom was a relatively difficult task, relative atomic masses were determined using the laws of chemical combinations and the compounds formed. Let us take the example of a compound, carbon monoxide, formed by carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with 4 grams of oxygen to form CO. In other words, carbon combines with 4 by 3 times its mass of oxygen. The atomic mass unit was earlier abbreviated as AMU, but according to the latest IUPAC recommendations, it is now written as U, which is unified mass. Suppose we define the atomic mass unit as equal to the mass of one carbon atom. Then we would assign carbon an atomic mass of 1.0 U and oxygen an atomic mass of 1.33 U. However, it is more convenient to have these numbers as whole numbers or as near to a whole number as possible. While searching for various atomic mass units, scientists initially took 1 by 16 of the mass of an atom of naturally occurring oxygen as the unit. This was considered relevant due to 2 reasons. Oxygen reacted with a large number of elements and formed compounds. This atomic mass unit gave masses of most of the elements as whole numbers. However, in 1961, for a universally accepted atomic mass unit, carbon-12 isotope was chosen as the standard reference for measuring atomic masses. One atomic mass unit is a mass unit equal to exactly 1/12 the mass of one atom of carbon-12. The relative atomic masses of all elements have been found with respect to an atom of carbon-12. Imagine a fruit seller selling fruits without any standard weights with her. She takes an orange and says this has a mass equal to 12 units. She makes 12 equal pieces of the orange and finds the mass of each fruit she is selling relative to the mass of one piece of the orange. Now, she sells the fruits by relative fruit mass units. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom as compared to 1/12 of the mass of one carbon-12 atom. Hence, if we were to define the atomic mass unit, we can say that an atomic mass unit is a unit of mass used to express atomic as well as molecular weights, equal to 1/12 of the mass of an atom of carbon-12. Or, the atomic mass unit is defined as 1/12 of the mass of an atom of carbon. Here are the atomic masses of a few elements. How do atoms exist? Atoms of most elements are not able to exist independently. Atoms form molecules and ions. These molecules or ions aggregate in large numbers to form the matter that we can see, feel, or touch. Now, if I ask you why is it not possible to see an atom with naked eyes, what do you think is the answer? Well, an atom cannot be visible to the naked eyes because atoms are minuscule in nature, measured in nanometers. Except for atoms of noble gases, they do not exist independently. What is a molecule? A molecule is in general a group of 2 or more atoms that are chemically bonded together, that is, tightly held together by attractive forces. A molecule can be defined as the smallest particle of an element or a compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or of different elements can join together to form molecules. Molecules of elements. The molecules of an element are constituted by the same type of atoms. Molecules of many elements such as argon, helium, etc. are made up of only one atom of that element. But this is not the case with most of the nonmetals. For example, a molecule of oxygen consists of two atoms of oxygen and hence it is known as diatomic molecule, O2. If three atoms of oxygen unite into a molecule instead of the usual two, we get ozone, which is O3. The number of atoms constituting a molecule is known as its atomicity. Metals and some other elements such as carbon do not have a simple structure but consist of a very large and indefinite number of atoms bonded together. Let us look at the atomicity of some nonmetals. Molecules of compounds. Atoms of different elements join together in definite proportions to form molecules of compounds. For example, hydrogen and oxygen, when combined in the ratio of 1:8 by mass, gives us water. Here are some other examples. Nitrogen and hydrogen, when combined in the ratio of 14:3 by mass, gives ammonia. Carbon and oxygen combined in the ratio of 3:8 gives us carbon dioxide. Refer to the table shown here for ratio by mass of atoms present in molecules and for atomic masses of elements. Find the ratio by number of atoms of elements in the molecules of compounds given in the table for atomic masses of elements. The ratio by number of atoms for a water molecule can be found as follows. Thus, the ratio by number of atoms for water is H:O is 2:1. The ratio by number of atoms for an ammonia molecule. Nitrogen ratio 14 by mass. Atomic mass is also 14, so mass ratio by atomic mass is 1. In case of hydrogen, it is 3. Thus, the ratio by number of atoms for ammonia is N:H is 1:3. Similarly, the ratio by number of atoms for carbon dioxide molecule is 1:2. What is an ion? If you're liking the video, don't forget to hit the subscribe, like and share button.
What is an ion? Compounds composed of metals and nonmetals contain charged species. The charged species are known as ions. Ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called anion, and a positively charged ion is called cation. Take, for example, sodium chloride. Its constituent particles are positively charged sodium ions and negatively charged chloride ions. A group of atoms carrying a charge is known as a polyatomic ion. Here are some polyatomic ions. Here are some ionic compounds. Writing chemical formula. A chemical formula identifies each constituent element by its chemical symbol and indicates the proportionate number of atoms of each element. That is, chemical formula of a compound is a symbolic representation of its composition. The chemical formula of different compounds can be written easily. For this exercise, we need to learn the symbols and combining capacity of the elements. The combining capacity of an element is known as its valency. Valency can be used to find out how the atoms of an element will combine with the atoms of another element to form a chemical compound. The valency of the atom of an element can be thought of as hands or arms of that atom. The rules that you have to follow while writing a chemical formula are: the valencies or charges on the ion must balance. When a compound consists of a metal and a non-metal, the name or symbol of the metal is written first. For example, calcium oxide, sodium chloride, iron sulfide, copper oxide, etc., where oxygen, chlorine, sulfur are nonmetals and are written on the right, whereas calcium, sodium, iron, and copper are metals and are written on the left. In compounds formed with polyatomic ions, the number of ions present in the compound is indicated by enclosing the formula of an ion in a bracket and writing the number of ions outside the bracket. For example, MgOH twice. In case the number of polyatomic ion is 1, the bracket is not required. For example, sodium hydroxide. Formula of simple compounds. The simplest compounds, which are made up of two different elements, are called binary compounds. While writing the chemical formula for compounds, we write the constituent elements and their valencies. Then, we must cross over the valencies of the combining atoms. The formula of hydrogen chloride would be HCl, whereas the formula of hydrogen sulfide would be H2S, because two atoms of hydrogen combine with one atom of sulfur. Formula of carbon tetrachloride would be CCl4 and aluminium oxide would be Al2O3. For magnesium chloride, we write the symbol of cation, which is Mg2+, first, followed by the symbol of anion, which is Cl-. Then their charges are crisscrossed to get the formula MgCl2. Thus, in magnesium chloride, there are two chloride ions for each magnesium ion. The positive and negative charges must balance each other and the overall structure must be neutral. Note that in the formula, the charges on the ions are not indicated. Calcium oxide. Here, the valencies of the two elements are the same. You may arrive at the formula Ca2O2, but we simplify the formula as CaO. Note that the formula of calcium hydroxide is CaOH twice and not CaOH2. We use brackets when we have two or more of the same ions in the formula. Here, the bracket around OH with a subscript 2 indicates that there are two hydroxy groups joined to one calcium atom. In other words, there are two atoms each of oxygen and hydrogen in calcium hydroxide. Here are some more examples. Sodium carbonate is Na2CO3. Brackets are not needed if there is only one ion present. Ammonium sulfate, on the other hand, is NH4 twice, so brackets are needed here, SO4. Let's do a quick recap. Let's see the formulas of sodium hydroxide, aluminium chloride, sodium sulfide, and magnesium hydroxide. Sodium oxide. It is an ionic compound made up of sodium ions and oxide ions. The sodium ion has a valency or charge of 1+, whereas oxide ion has a valency of 2-. Hence, the formula of sodium oxide is Na2O. Aluminium chloride is an ionic compound made up of aluminium ions and chloride ions. Aluminium ion has a valency of 3+, whereas chloride ion has a valency of 1-. Hence, the formula of aluminium chloride is AlCl3. Sodium sulfide is an ionic compound made up of sodium ions and sulfide ions. Sodium ion has a valency of 1+, sulfur ion has a valency of 2-. Hence, the formula of sodium sulfide is Na2S. Magnesium hydroxide. It is an ionic compound made up of magnesium and hydroxide ions. Magnesium ion has a valency of 2+ and hydroxide has a valency of 1-. Hence, the formula of magnesium hydroxide is MgOH twice. Let's see the names of compounds like aluminium sulfate. Al2O3 is aluminium sulfate. It is an industrial chemical used as a flocculating agent in the purification of drinking water. CaCl2 is calcium chloride. It is widely used as an additive in plastics, wastewater treatment plants. K2SO4 is potassium sulfate. It is the preferred fertilizer for specific kinds of crops. KNO3 is potassium nitrate. It is a strong oxidizer used especially in making gunpowder, as a fertilizer, and in medicines. CaCO3 is calcium carbonate. It is a medication used to prevent or treat low blood calcium levels and also an antacid. CaCO3 is calcium carbonate. CuNO3 twice is copper nitrate. It is used as a mordant and oxidizing agent in textile dyeing. Can you tell me how many atoms are present in a H2S molecule? Well, in an H2S molecule, 3 atoms are present in total. 2 are hydrogen and 1 of sulfur. Hydrogen sulfide gas is colorless with the repellent odor of rotten eggs. PO4 3- is a chemical derivative of phosphoric acid with the chemical name phosphate, also called phosphate ion or orthophosphate. In a PO4 ion, 5 atoms are present in total. Amongst 5, 1 is of phosphorus and 4 atoms are of oxygen. It is naturally found in food, human bodies, and water. Molecular mass and mole concept. The molecular mass of a substance is the sum of the atomic masses of all the atoms in a molecule of the substance. It is therefore the relative mass of a molecule expressed in atomic mass units. Let's see the relative molecular mass of water. Atomic mass of hydrogen is 1U and atomic mass of 2 hydrogen therefore would be 2U. Atomic mass of oxygen is 16U, therefore the molecular mass of water is 2 plus 16, that is 18U. Now if we calculate the molecular mass of HNO3, we'll see that the atomic mass of hydrogen is 1U, nitrogen is 14U and oxygen is 16U. Since there are 3 atoms of oxygen, the total mass is 48U. Hence, the molecular mass of HNO3 would be 1 plus 14 plus 48, which makes it 63U. Formula unit mass. The formula unit mass of a substance is a sum of the atomic masses of all the atoms in a formula unit of a compound. It is calculated in the same manner as we calculate the molecular mass. The only difference is that we use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride has a formula unit NaCl. Its formula unit mass can be calculated as 1 into 23 plus 1 into 35.5. 23 is the atomic mass of sodium and 35.5 is the atomic mass of chlorine. So, the total mass is 58.5U. The formula unit mass of calcium chloride. The formula of calcium chloride is CaCl2. Its formula unit mass can be calculated as atomic mass of calcium plus 2 times the atomic mass of chlorine. So it is 40 plus 2 times 35.5, which makes it 111U. Let's calculate some more molecular masses. The molecular mass of hydrogen H2 is 2 times the atomic mass of H. Similarly, molecular mass of O2 would be 2 times the atomic mass of O. Cl2 would be 2 times the atomic mass of Cl, and CO2 would be atomic mass of C plus 2 times the atomic mass of O. So on and so forth. If you're liking the video, don't forget to hit the subscribe button and click on the like and share button as well. Mole concept. Take an example of the reaction of hydrogen and oxygen to form water. 2H2 plus O2 gives 2H2O. The above reaction indicates that 2 molecules of hydrogen combine with 1 molecule of oxygen to form 2 molecules of water, or 4 units of hydrogen molecules combine with 32U of oxygen molecules to form 36U of water molecules. We can infer from the above equation that the quantity of a substance can be characterized by its mass or the number of molecules. But a chemical reaction equation indicates directly the number of atoms or molecules taking part in the reaction. Therefore, it is more convenient to refer to the quantity of a substance in terms of the number of its molecules or atoms rather than their masses. So, a new unit, mole, was introduced. The mole, the symbol is MOL. It is the SI unit of the amount of substance. 1 mole contains exactly 6.02214076 into 10 raised to the power 23 elementary entities. This number is the fixed numerical value of the Avogadro constant Na when expressed in the unit 1 by mol and is called the Avogadro number. Avogadro constant or Avogadro number was named in honor of Italian scientist Amedeo Avogadro. The amount of substance, symbol N, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, or any other particle, or maybe specified group of particles. The mole is the amount of substance of a system that contains 6.02214076 into 10 raised to the power 23 specified elementary entities. 1 mole of anything is 6.022 into 10 raised to the power 23 in number, as 1 dozen equal to 12 numbers and 1 gross equal to 144 numbers. Let's talk about the relationship between mole, Avogadro number, and mass. Besides being related to a number, a mole has one more advantage over a dozen or a gross. This advantage is that mass of 1 mole of a particular substance is also fixed. The mass of 1 mole of a substance is equal to its relative atomic or molecular mass in grams. The atomic mass of an element gives us the mass of one atom of that element in atomic mass units. To get the mass of 1 mole of atom of that element, that is molar mass, we have to take the same numerical value but change the units from U to G. Molar mass of atoms is also known as gram atomic mass. For example, atomic mass of hydrogen is 1 U. So, gram atomic mass of hydrogen is 1 gram. 1 U hydrogen has only 1 atom of hydrogen. 1 G hydrogen has 1 mole atoms, that is 6.022 into 10 raised to the power 23 atoms of hydrogen. Similarly, 16U oxygen has only 1 atom of oxygen. 16 gram oxygen has 1 mole atoms, that is 6.022 into 10 raised to the power 23 atoms of oxygen. To find the gram molecular mass or molar mass of a molecule, we keep the numerical value the same as the molecular mass, but simply change units as above from U to G. For example, as we have already calculated, molecular mass of water is 18U. From here, we understand that 18U water has only one molecule of water. 18G water has 1 mole molecules of water, that is 6.022 into 10 raised to the power 23 molecules of water. Chemists need the number of atoms and molecules while carrying out reactions, and for this, they need to relate the mass in grams to the number. It is done as follows. 1 mole is equal to 6.022 into 10 raised to the power 23 number. Relative mass in grams. Thus, a mole is the chemist's counting unit. The word mole was introduced around 1896 by Wilhelm Ostwald, who derived the term from the Latin word moles meaning a heap or pile. A substance may be considered as a heap of atoms or molecules. The unit mole was accepted in 1967 to provide a simple way of reporting a large number, the massive heap of atoms and molecules in a sample. Let's calculate the number of moles for the following. 52 gram of helium. Now we know that number of moles is equal to given mass divided by molar mass. Molar mass of helium is 4 grams and given mass is 52 grams. So we have 52 divided by 4, which is 13 moles. If there are 12.044 into 10 raised to the power 23 number of helium atoms, how do we find mole? Now we know that 1 mole is 6.022 into 10 raised to the power 23 atoms. So, number of moles is given number of atoms divided by Avogadro number, which gives us 2 moles. Similarly, for 0.5 mole of nitrogen gas, mass is equal to molar mass into number of moles. We are given 3.011 into 10 raised to the power 23 number of nitrogen atoms. So to calculate the number of moles, we divide the given number of particles by Avogadro number. So on and so forth. Let's practice some more questions to get a better understanding of the concepts. If 1 mole of carbon atoms weigh 12 grams, what is the mass of 1 atom of carbon? 1 mole of carbon atoms weigh 12 grams and we have to calculate mass of 1 mole of carbon atoms, that is 12 gram. Then mass of 6.022 into 10 raised to the power 23 number of carbon atoms is 12 grams. Therefore, mass of 1 atom would be 12 divided by 6.022 into 10 raised to the power 23. Which has more number of atoms, 100 grams of sodium or 100 grams of iron? We are given that atomic mass of sodium is 23 and iron is 56U. Atomic mass of sodium is 23 and iron is 56. Then gram atomic mass of sodium would be 23 grams. Now 23 gram of sodium contains 6.022 into 10 raised to the power 23 gram number of atoms. 100 grams would be 6.022 into 10 raised to the power 23 divided by 23 times 100. Similarly, we calculate 100 gram of iron contains 1.0753 into 10 raised to the power 24 number of atoms. Therefore, sodium contains more number of atoms as compared to iron. A 0.24 gram sample of compound of oxygen and boron was found by analysis to contain 0.096 gram of boron, and 0.144 gram of oxygen. Now we have to calculate the percentage composition of the compound by weight. We know that the total mass of the compound is 0.24 grams and mass of boron in it is 0.096 grams. Therefore, percentage composition by weight of boron is mass of boron divided by total mass of the compound into 100, which gives us 40%. Now mass of oxygen in the compound is 0.144 grams. Therefore, percentage composition would be 60%. The compound is made up of only boron and oxygen because the total composition is 60% plus 40%, that is 100%. When 3 gram of carbon is burnt in 8 grams of oxygen, 11 gram of carbon dioxide is produced. What mass of carbon dioxide will be formed when 3 gram of carbon is burnt in 50 grams of oxygen? And which law of chemical combination will govern here? This is a very interesting one. We know that C plus O2 gives us CO2. As per the given condition, when 3 gram of carbon is burnt in 8 gram of oxygen, 11 gram of carbon dioxide is produced. So 3 gram plus 8 grams gives 11 grams. Total mass of reactants is mass of carbon plus mass of oxygen, which is 11 gram. Now total mass of reactants is equal to total mass of products. Therefore, the law of conservation of mass is proved. Then, it also depicts that the carbon dioxide contains carbon and oxygen in a fixed ratio by mass, which is 3:8. Thus, it further proves the law of constant proportions. Now, 8 gram of carbon must 3 gram of carbon must also combine with 8 gram of oxygen only. This means 50 minus 8, which is 42 gram of oxygen, will remain unreacted. The remaining 42 gram of oxygen will be left unreactive. In this case also, only 11 gram of carbon dioxide will be formed. The above answer is governed by the law of constant proportions. Now, give the names of the elements present in the given compounds. Quicklime, hydrogen bromide, baking powder, and potassium sulfate. Quicklime is CaO, and the elements present are calcium and oxygen. Whereas hydrogen bromide is HBr, and the elements present are hydrogen and bromine. Baking powder is K2SO4. Elements present are potassium, sulfur, and oxygen. Potassium sulfate is NaHCO3, and the elements present are sodium, hydrogen, carbon, and oxygen. Calculating the molar mass. Here are some examples of the calculations of molar mass. For example, ethine, which is C2H2. The molar mass would be 2 times the atomic mass of carbon plus 2 times the atomic mass of hydrogen, which makes it 26 grams. Similarly, we calculate the molar mass of the other compounds. Now, what is the mass of 1 mole of nitrogen gas? It will be 1 into mass of nitrogen, which is 1 into 14, which is again 14 grams. 4 moles of aluminium atoms would be 4 times 27. 10 moles of sodium sulfite, Na2SO3. It will be 2 times the mass of sodium atom plus 1 times the mass of sulfur plus 3 times the mass of oxygen atoms. If you remember, a mole is defined as the amount of a substance that contains exactly 6.0221476 into 10 raised to the power 23 elementary entities of the given substance. Now converting into mole. Let's convert 12 gram of oxygen gas into moles. We know that 32 gram of oxygen gas is 1 mole. So 1 gram of oxygen gas would be 1 by 32 moles. Given is 12 grams. So it will be 12 by 32. Similarly, we can calculate the number of moles for 18 grams of water, 44 grams of carbon dioxide as shown here. Mass of 1 mole of oxygen atoms is 16 grams, then the mass of 0.2 moles of oxygen atoms would be 0.2 times 16. Let's calculate the number of molecules of sulfur present in 16 grams of solid sulfur. The molecular mass of the sulfur molecule is 32 into 8. 1 mole of sulfur molecules is equal to 256 grams. This means 256 grams of solid sulfur contains 6.022 into 10 raised to the power 23 molecules. Then 16 grams of solid sulfur contains 6.022 into 10 raised to the power 23 divided by 256, which is 16 molecules, which is equal to 3.76375 into 10 raised to the power 22 molecules. Let's calculate the number of aluminium ions present in 0.051 gram of aluminium oxide. The mass of an ion is the same as that of an atom of the same element, and the atomic mass of aluminium is 27U. Now, molar mass of Al2O3 is 2 times the mass of O, 2 times the mass of aluminium plus 3 times the mass of oxygen. 1 mole of Al2O3 contains 2 moles of aluminium ions. So 102 grams of Al2O3 contains 2 into 6.022 into 10 raised to the power 23 aluminium ions. Hence 0.051 gram of Al2O3 will contain 2 into 6.022 into 10 raised to the power 23 divided by 102 times 0.051. Chemistry states the more energy you put into a bond, the harder it is to break. Keep learning, keep growing. Remember, life is what you make it. Keep watching I Say Kids. Do subscribe to the channel and hit the like button so that we are inspired to make good videos for you awesome viewers. Take care. Have a lovely day. Bye-bye.